And next up is Dalia Grendaitė from Vilnius University. So Dalia, the floor is yours.
So hello all. Thank you for inviting me to this event. I'm a PhD student at Vilnius University in Lithuania. And today I will give a talk about my work on lake water quality assessment using remote sensing and machine learning. So to begin with,
Dalia, your slides. Yeah, thank you.
Yes, to begin with, I will briefly describe the current state monitoring system in Lithuania. So we have 357 lakes and ponds that are monitored within the program, and they are larger than half a square kilometer. Most of them are concentrated on the eastern side of Lithuania, as you can see in the image, where the Baltic uplands are. And during years 2015 to 2020, 308 lakes and ponds were monitored, and around 60% of the water bodies are of good and high ecological status based on water transparency data, while 26% are bad and moderate class, so they are not sufficiently good as aimed by the European Union Water Framework Directive. And of 14%, the status is unknown, or we may have some older than 6 years data. Some water bodies suffer from strong algal and cyanobacteria blooms that in some cases are even toxic, and therefore water should not be used from such water bodies. For these cases, we need better management, and better management starts with good monitoring. Therefore, using remote sensing may help to have more frequent and larger areas covering observations. However, remote sensing data also come with some uncertainties. One of the largest is from atmospheric influence. So to be able to use remote sensing data effectively and reliably, we need well-performing atmospheric correction algorithms and good parameter retrieval algorithms. Therefore, to show uncertainties emanating from the selection of atmospheric correction algorithm to the retrieval of water quality parameters such as chlorophyll concentration, we performed a test with several different architecture commonly used atmospheric correction algorithms, such as Ecolite, Centocore, ICOR, Polymer, and C2RCC. And ESTHub processing platform was really helpful in implementing these algorithms, as Centocore, Polymer, C2RCC is there in the processing platform. So it was really easy to use it to apply it on the 7 images, 7 different images on a tile in the eastern Lithuania that covers 136 lakes. And also for this research, we used 10 different architecture chlorophyll retrieval algorithms. They were based on 2 or 3 bands and had, as you can see, some of them are band difference algorithms, some algorithms use band ratios, and all this was calculated on Sentinel-2 data. So when we retrieved the chlorophyll concentration for all 136 lakes, we saw a great variation among the atmospheric correction algorithms and also the chlorophyll algorithms. From monitoring data, we expected values from 0 to 150 micrograms per liter. And we can see that image-based algorithms such as Ecolite, ICOR, and Centocore gave quite similar results. However, using different algorithms of chlorophyll provided really different results. And you can see here that the 1st and the 10th algorithm provided quite similar results when different atmospheric correction algorithms were used. And So we can see that high uncertainties of reflectance transferred to chlorophyll concentration retrieval. And here you can see the matchup analysis where you can see the in situ data and also retrieved chlorophyll data from Sentinel-2 data. And nonetheless, testing different chlorophyll concentration algorithms showed that some band configurations, such as band difference algorithms that use either 2 or 3 bands, were less dependent on the atmospheric correction product selection and provided closest to in situ chlorophyll concentration, regardless of the atmospheric correction product used. And also, we noticed that some algorithms and atmospheric correction products showed relatively higher bias for lower chlorophyll concentrations, lower than 10 micrograms per liter, and deriving algorithms for groups of lakes could actually improve the chlorophyll concentration retrieval from Sentinel-2 data. So moving on to the classification, we aim to classify inland waters to water types based on the often routinely measured according to monitoring programs water quality parameters such as transparency, chlorophyll concentration, and suspended matter data. And here we aim to create a data-driven model that use machine learning methods and assign a lake to a class that is defined by these water quality parameters. This method could be used in environmental protection agencies and could give first data on the status of the water body, and also could be used for optimization of the monitoring program. And here we used data from 2015 to 2019. From these years, we found 458 matchup data. And we distinguished 4 classes here. Here in this table, you can see the characterization of these classes. So Clear Lake class is defined by good transparency value that is related to high or good ecological status based on this parameter. And also it is characterized by low chlorophyll concentration and low suspended matter concentration. And you can see here that such cases were 209 cases. And in the beginning, we actually tried to make a simpler model to separate only 2 classes. So this Clear Lake class from other lakes. And these other lakes, as you can see in the lower table, they have higher concentrations of optically active substances, and one of them is characterized by medium concentration of chlorophyll, this moderate class, and then 2 other classes are characterized by lower transparency values, and one class, this is mostly related to chlorophyll, and in another class, the chlorophyll concentration is low. So today we'll talk only about the 2 class problem, only separating the clear class and other class. And so we used, so to use a machine learning model, we need input features of objects so that we could get a class of an object. So here we tried to use only spectra from remote sensing data from Sentinel-2, and we selected different features from spectra. So we took the reflectance amplitude, we calculated some band ratios, and we also used some several parameters that can be derived from several bands. So for example, hue angle, which is related to water color. It is calculated based on 4 bands. So it's kind of integrating more information than only if we used 1 band, for example. And also we used month data as a feature, as we thought that this could help actually to separate lakes where we have some strong algal blooms. So we used several machine learning algorithms, such as logistic regression, support vector machine, and several ensemble methods. For example, random forest. And here you can also see the model performance metrics, which are well commonly used to evaluate the models. And so after testing these 5 machine learning algorithms, based on this data, we saw that actually the models, they provide quite similar results. If you look at the accuracy data, for example, you can see that there's not huge differences, but random forest actually provided the best accuracy when we applied it on the test set. And also this AUX score is commonly used, and it also very well represents the model's ability to classify. So here we have 0.9 for random forest, and for the test set we have 0.85, so which is a really good estimate actually. As if it was 0.5, sorry, it would be, well, a random guess, and if it was 1, then it would be a perfect model. But well, we don't want a perfect model because it will lose the ability to generalize. So at first we tried to evaluate models without any hyperparameter tuning. That is also an important part in machine learning when we prepare algorithms. However, well, since we got quite good estimates, we then tried to actually tune the hyperparameters, but the results actually were not improved that much, or we can say that it wasn't improved at all. Since we got really similar parameters here. So actually model performance here more depends on the data, on how we split it into training and test sets, rather than on the hyperparameter tuning. So actually, well, it's a good thing because we can save some time here and not to spend it on hyperparameter tuning. And when we use random forest, we can actually check which features were most often used in the random forest algorithm. And so here you can see that actually the most important feature was the band ratio of green and red edge band. Also the derived from 4 bands parameter hue angle, and also the band ratio, which is often used for chlorophyll retrieval, the red edge band and red band ratio. And for example, month data actually in this case didn't help that much to separate those algal blooms as I expected. So coming to conclusions, what I want to emphasize here, that such a data-driven approach where we use only remotely sensed data and input in a model as features, this could be used actually in those areas where in situ spectral data is not available or is very scarce, and from that data we cannot make a model. So in this case, when we have measurements from state monitoring programs, we can actually make such model which is only data driven and get quite good results. And this could be used, as I mentioned, in environmental protection agencies. This could be really helpful information to optimize their monitoring programs. And also what I want to mention here is that when we have this classification, we can also derive the water quality parameters, and so we can get more accurate data. So that's all from me today. Thank you all for listening.